Expect this exam to be 40 questions, 1 hour long. We don't have any particularly long questions yet. So it will be, can you have a page of notes? Can you bring notes? How much notes? 1 page, front and back? Front and back, yeah. I will provide you a periodic table. It'll be part of the exam packet, along with an answer sheet that you bubble in, okay? You'll need a pencil to bubble it in. Don't use a pen, it tends to cause problems. I use that scanning app to do it, so I can get your answers back fairly quickly. What I will do is on exam 1, I'll actually post a sheet to exam 1, which you can use, or I'll hand them out. We'll see if I can get them to post properly as feedback to each of you. But that sheet will have a code on it, and you can actually use that code to see your raw scores, okay, whenever I release them after everybody's taken the exam. Okay? And then I'll post the exam up there whenever everybody's taken the exam, so you guys can like match those up. It'll show you which ones you got wrong, what the correct answers were. Okay. Okay. Anybody have any questions? Yes, you can have a scientific calculator. Yep. Not anything that can connect to the internet. Okay. No internet, no AI, none of that sort of stuff. Actually, we've had so many academic cases lately with AI and internet stuff where one person like was paying somebody to do a class for them, the online thing, which is actually the old school method. I'm kind of proud of that person for going old school. Yeah. Huh? Yeah, the reason he got busted actually in this case was, anyways, we can talk about it some other time. So the carbon has to have 4 bonds, single bonds. We can do 4 single bonds. We can do a double bond. We can do a triple bond. You could do 2 double bonds. This right here is the examples. Remember, though, that it has to form a full octet because that's how many bonds carbon wants for a full shell. This right here are the different groups and their typical bonding patterns. Right here you see the hydrogen single bond. This is the nitrogen. Notice the nitrogen can form a triple bond. And then right here we see the double bond for the oxygen, which again can form a double bond. Anybody have any questions about that so far? Okay. You don't actually see sulfurs with double bonds very often because they're very big. It's a little harder to make double bonds with them. It can happen, just very unlikely any of you will see it unless you go into chemistry. Okay? Right, so the molecular formula for a covalent compound is going to identify all the components in a molecule. So glucose, for example, has a formula C6H12O6. That is 6 carbons, 12 hydrogens, 6 oxygen atoms. If we change those numbers in any way, is that glucose? If we double these numbers, 12, 24, 12, is that glucose? No, that would be a completely different sugar. Okay, in fact, there are sugars that are that. They're called disaccharides. Okay, if we had a number here, we divided everything by 6. Would that be glucose? No. Glucose, by the way, is the sugar that your brain uses. It's almost all of the energy in your brain is actually provided by glucose. So right here, that is glucose. If you change this in any way, it is not glucose. Okay, it would actually change the molecular formula, and it would be a different compound. In fact, the C1H2O1 is actually a compound that happens in your body. It can be a little bit toxic at times, but it's usually handled fairly quickly in your body, and it's not a huge problem, usually. So notice what it doesn't do is give you any idea what this looks like. Okay? You know what is in it. You have no idea what it actually looks like, right? And so we oftentimes need a way to actually figure out what it looks like, and this is going to be what we were doing just a little while ago, which is our Lewis structures, right? And so this is the CH4 we did, which is our Lewis structure. Notice right here, that's the steps for Lewis structure. I took you through a slightly different series of steps because mine's more complete. Okay? So this is actually what is in your book. Right? Now, I highly recommend using my methodology to do it because you'll never have to guess and figure out whether it's double bonds or not. You always know at the end whether it had a double bond or not. So let's talk about binary compounds and their naming. So when you're looking at a binary compound, this is going to consist of only two elements. That's the binary. And this is going to have the first element in the formula is you're just going to straight up name that. So let's say we had, last time I had started on dihydrogen monoxide, right? Okay. So dihydrogen would be two hydrogens, right? We start with just hydrogen first. And then oxide is for the oxygen, right? And that's the second one here. Okay. And then we're going to designate the numbers using the Greek prefixes. Technically, you don't actually have to put the monoxide. If you just have one, you can oftentimes skip that. But if you want to be complete about it, you can put both. So dihydrogen monoxide. This one here is commonly known as water, and so we typically call that just water. And you very rarely would ever use dihydrogen monoxide. Only if you want to be like, try and sound smart. Or we want to trick people, right? Okay. Funny story is I told you the last time about how like dihydrogen monoxide kills more people than any other compound in the world, has a 100% addiction rate. More people overdose on dihydrogen monoxide than every other drug in the planet combined. Okay. Did I tell you all that last time? Okay. We should totally ban it, right? Okay. Petitions have happened repeatedly throughout the years to ban dihydrogen monoxide. Like people joke around and then this actually goes on and on and on. The most extreme version of this is Arizona State Senate once had a bill that they were actually writing to ban dihydrogen monoxide. I believe that this was the 70s, if I remember correctly, before the internet. And somebody played this joke and it went a little too far. And finally somebody managed to get through to them, hey, that's water. Which just, wow, right? So if you ever wonder how well government understands science, pretty much not at all. All right. So this right here is nitrous oxide. You probably have heard that before. No? Maybe? Oh, okay. Like laughing gas and stuff. Okay, those are known by the traditional names typically. Right here are the prefixes. Those are the Greek prefixes. This is mono, meaning one, like monocycle. Di, meaning two. Di and bi are actually the same thing, just pronounced differently in English. Tri, like tricycle 3. Tetra 4. Penta 5. Hexa 6. Hepta 7. Everybody okay with that? Okay, so this right here is sort of the flow chart you have probably developed in your head so far of how to name things. We first need to look, is it ionic or is it covalent, right? Because that's going to play a major difference here. It's ionic, it has ions, right? If it's covalent, it's not ions. So you don't have to name it like ions. So, how do we tell which one's which usually? Especially for like this class. Yeah, we look at, like, let's say I give you a random thing, okay? So like KCl. Or another way of saying that is you look if they're a metal and a non-metal, or versus a non-metal, non-metal pair, right? Yeah. So if it's a metal and a non-metal, then it's going to be ionic probably. If it's non-metal pair, then it's likely going to be covalent. Okay? So if you don't have any metal, you probably have covalent. Almost certainly for you guys. If you have a metal, it's probably going to be ionic, right? Almost certainly ionic for you all. Okay. If that goes out again, I'll switch back to my deal. Let me know, okay? Because I don't always see. All right, so again, ionic. This is going to be, is it group 1A, 2A, or 3A metals? If it's groups 1A, 2A, and 3A metals, then it is for certain ionic. Okay, let's see if this switches. Okay. That video must be really weak. That's all I can think. Okay. So, if it's anything else, it's pretty much always covalent, okay? So especially if it's both non-metals. If everything's non-metal, covalent. Now the other part is, if it's ionic, then does it use Roman numerals? So if it is one of the group 1A, 2A, and 3A, it's going to use Roman numerals only, right? It's not going to use Roman numerals. Excuse me. Wow. Got thrown off by having to reconnect. If it is not one of those three groups right there, if it's a metal that's not in one of those three groups, it needs a Roman numeral, okay, of some sort. Okay. Now let's talk about moles. Has anybody ever heard of moles? Okay. Does anybody know when Mole Day is? There'll be a cool speaker on Cumberland campus. I'll post more details when more details come available, but it'll happen on Mole Day. Mole Day being 10/23. Okay? All right, so moles are going to relate the mass of an element in grams to the number of atoms it contains. So it's going to be a unit that's grams per mole. That will relate that molar mass. That's what that is on periodic table. And what moles do is it's like a package, okay? So you go to the store, you buy a dozen of cans of soda, right? When you get one package of soda, there's a dozen cans in it, right? Okay. You buy a package of a dozen donuts. How many donuts did you get? A dozen, which is 12, right? Okay, so think of moles like that. They're like packages, okay? And what they are is they are the number that needs to be true for the periodic table to be in atomic mass units, like we had talked about before, and that number also to be related to grams, okay? And so it's the conversion factor between those. It's relating the AMUs to grams. So again, like a dozen, this could be a package of eggs. You could have a mole of eggs. That would be a lot of eggs. Do not buy a mole of eggs. You could have a mole of pennies. You could have a mole of anything. Okay. Typically, we're going to be talking about moles of atoms, moles of particles, or moles of molecules. Okay. But again, it's just a package, just one of those set package numbers, like a dozen. Okay. All right. So again, keep that in mind, that it works just like a dozen would. If I have 2 dozen, I have how many? 24. 3 dozen, 36, right? 4 dozen, 48. So if I have 1 mole, then I'm going to have that mole amount, which is called Avogadro's number. Okay? If I have 2 moles, then I'm going to have double that amount, right? And so on. I'm trying to avoid the actual number so far because I want you to conceptually understand that it's actually just that easy. Even though it's going to be this really long number, and you're going to go, oh my goodness, Dr. Clausen, that seems tough. It's not. It's the exact same math you just did for dozens. Okay? It's just a much more complicated number. Don't be intimidated. Just step back, breathe easy. Deep breaths. Okay? Okay, so now this number actually is derived from carbon-12, by the way. So what you'll notice here is that if you have 12 grams of carbon-12, then you're going to have 1 mole of that carbon-12. Okay? Just like if you were to have one package of a dozen, you would have 12 eggs, right? You have 12 eggs, you had a package of a dozen, didn't you? Okay. Now, note that we actually can do the same sort of math with eggs as we're going to do with this number, okay? So if every egg weighs 60 grams, how can we tell how much weight in eggs there is? Well, you just take 12 times 60, right? That's it, okay? You already knew that, didn't you? Like, that's not intimidating. So remember that when you look at this number, you're being intimidated because it's a longer number, okay? It's not because the math changed, right? Okay, let's go ahead and look. So this is it with all the zeros. That's Avogadro's number, okay? So the number, Avogadro's number, it actually would go on, but we're just going to give you the one with 3 significant figures, is 6.02 times 10 to the 23rd. I would recommend just sort of memorizing that number. I will give it to you. You'll notice it's on the, I think it's on the periodic table I give you actually at the beginning of class. Typically it is on those. So 6.02 times 10 to the 23rd, you're going to use this number by the end of the semester enough times that you're just going to have it memorized. Just because it's going to save you time. Okay? If you go ahead and memorize it now, it'll probably save you time. Now, 1 mole of any element is going to have what's referred to a molar mass in grams. Okay? That's actually going to be numerically equal to the number that's on the periodic table. Remember that mass number on the periodic table? Yeah. That numerically is a molar mass. Okay? Specifically, that would be an atomic mass because you're looking at an atom. Right? Okay, so molar mass, the amount of mass that a mole of that substance would have. Okay? So again, where would you look for these molar masses on the periodic table? What would be the molar mass of hydrogen? So we look at the hydrogen. It's 1.00075. Did I get it? Yep. And that's the molar mass of hydrogen, right? We look on the periodic table. Carbon is 12.01, I think. Was that correct? Let's not do this anymore because I don't think I can get it at the end. We'd have to see if I can get any of the other ones right. All right. So again, that's the molar mass. If you have that number of grams of any of those elements, then how much do you have? You have a mole, right? Okay. Okay, so that also is the AMU, atomic mass units, isn't it? This number here is that conversion factor between the two. That number has to be that to be true. Okay? Now again, this is the number of particles, atoms, or molecules in a mole, right? So you have 6.02 times 10 to the 23rd atoms in a mole. Okay? Okay. If you had a mole of eggs, how many eggs would you have? A mole. You have 6.02 times 10 to the 23rd, don't you? Okay? Or Avogadro's number. If you had a mole of pennies, you'd be very happy because you'd have 6.02 times 10 to the 23rd. Okay? So you just need to make sure that in your brain, when you hear mole, package, that package has how many items in it? Avogadro's number 6.02 times 10 to the 23rd. Okay? Just like when you hear dozen, you automatically go 12. Right? This is your new package. This is Avogadro's number. This was actually named in honor of the Italian physicist, which is Amedeo Avogadro. I cannot do Italian well. Obviously not Italian, right? Again, this is the number of atoms if you have a mole of atoms. Again, if you had bowling balls, eggs, it doesn't matter. Silver atoms, molecules of water, they're all the same things, right? Doesn't matter because 1 mole of anything is Avogadro's number of those items. Okay? Huh? Yeah, this number goes out. If you look it up, it actually goes out much further. Yeah. And every few years, they actually get another decimal place on it. So, yeah. It is not an exact number because we came up with AMU and grams completely separately. Yeah. They weren't defined off each other. We probably really should redefine the gram off of atomic masses in some way. that would probably be smart, but there's a lot of things that units could do to be smarter. So sometime around we should talk about it because it's actually kind of a cool thing. You can actually do a completely unitless numbers. They're from galactic constants. So they're from constants of the universe instead. Yeah. And it actually would be really cool, but you'd have these weird numbers. So like some of your numbers, would it be like 10 to the 30 somethings? And that would be everyday like weights and stuff. And you'd have other numbers that you'd always have to do like 10 to the negative 20 somethings for everyday amounts. And so nobody wants to do it. Okay, so this is that conversion factor that you can use. Remember, the equalities can be converted into conversion factors, right? And so we had an equality, 6.02 times 10 to the 23rd is 1 mole, right? And so that can also be used as a conversion factor. That's what we're seeing here. The formula mass versus the formula weight. There is a difference. Molar mass is going to be where you have molecules. Formula weight is going to be used when you have the sum of the atomic masses, and typically is going to be used when you have things like our ionic compounds, because they don't have just 2 sets. They can be hundreds of sets. Okay? And so really what you're giving is just the ratio. You're not giving specific molecules. Okay? Now, the molar mass of a compound is going to be numerically equal to the formula weight. So if you figure out either of those, you're going to have the same numbers. Okay? They're going to be grams per mole. There is another unit to complicate this slightly, which is called Dalton. Blame this on the biologists. Apparently, they didn't get the memo that somebody had already come up with AMU like 100 years before them. And they decided to just go ahead and make another unit, Dalton, DA, which is the AMU, and purely is just used because we're in biochemistry. So that's typically what like proteins and enzymes, which are usually proteins, RNA, DNA are measured in Daltons typically. And it is purely an AMU number, and it has no difference. Okay. Also has the exact same rules as AMU, so you could go grams per mole, right? And it would be the same numerically, just change the unit. So don't ask me why that decision got made. I will never get that one. All right, so this right here again is Lewis structure for methane. Notice the Lewis structure actually looks flat, but in reality, this is not flat. So this is going to be what's called Vesper, okay? And what we're going to do is we're going to take these structures, and remember that each of these domains, each of these electron domains, are repelling each other, right? So they're going to want to separate the maximum amount they can around a single point. And so realistically speaking, these things all look like you took balloons and tied the stems together with that number of balloons. So if you were to tie 4 stems of balloons together, you would get this shape right here. Notice it looks like a camera stand. Everybody see that? Why would it look like a camera stand? Because camera stands want maximum separation, don't they? They want the most sturdy base they can have to hold the highest camera they can, right? So it looks like a camera stand. And that is called tetrahedral right there. It has a 109.5 angle. And can everybody see that, how that is three-dimensionally? This one comes out towards you. That one fades away from you. That one's in the plane. Right here is in the plane of the screen. Okay. This right here is wedge dash formula. So what we've done here is the ones that are in the plane of the screen or paper are written with just bonds, normal bonds. And so those ones are flat. See that hydrogen, carbon, hydrogen right there are flat. Okay. And the one that's coming out towards you, so this is coming out from the screen towards you. And this one has what's called a wedge. And notice it's just like you do three-dimensionally, right? It's darker as it comes out towards you, as if it's like jutting out and hit you. Okay? And then the one that has hatching here, this is the dashes, that's fading away from you. So that one is back into the plane, past the plane of the screen. Okay? It's going away from you. Notice that's the same structure as that one is then. These are the same thing. That's just rewritten with wedge dash right there. Okay? Okay. This right here is what VSEPR actually stands for. It's valence shell electron pair repulsion model. That's what VSEPR stands for. Realistically, what you need to do is be able to actually use it. And so what it's always going to be is maximum separation. So how do we figure out the shape of that molecule? Remember how I was calling them electron domains, and I said your book calls them like charge clouds, electron clouds, that sort of thing? So this is what your book calls them: charge clouds or bonding clouds and non-bonding clouds. Okay? Again, I call them domains. Everybody go with domains? Everybody understands what I'm referring to the same thing? Spaces electrons are going to occupy. Okay? Okay. Now, when we're talking about electron domains, there's the ones that are occupied with bonds, right? Like a double, triple, single bond. Those are all single electron domains, right? And they're what's referred to as bonding domains, okay? Or bonding clouds or bonding, I think they use clouds in this book only. Some books use multiple, which is a whole nother level. Anyways, then there's non-bonding domains. Remember how I talked about the lone pairs? And like we had talked about a single electron could be one of these, a non-bonding domain. Okay, so the reason I was having you practice and figure out how to count the number of domains is that we need them to figure out what the shape around a central point is. Okay? And so right here, if you have 4 domains around a central point, that's going to be a tetrahedral shape. Can everybody say okay? Looks like the camera stand, right? Okay. This right here is if we have 4 domains, then again, 4 domains is going to be a tetrahedral shape for the electrons. But there's a difference between if the thing on the end of it is a lone pair, non-bonded, versus bonded. Okay? And this difference is a difference in terminology. So what we have here is we have the electron geometry. So for the electron geometry for this one would be tetrahedral. Okay? And that would be the geometry of the electrons, right? The molecular geometry, the geometry of the molecule, i.e. the atoms, right? This is going to be referred to as trigonal pyramidal, okay? Which is the one labeled pyramidal. Okay? Has a base that's triangles in that. And if you don't look at the electron part, this looks like a pyramid. water, by the way, in case you're wondering. And what you're going to see here is that, again, the electron geometry is what? What's that electron geometry look like? Come on, folks. You can do it. Looks like this one, doesn't it? Just laid on side. And this one. These are all tetrahedral for electron geometries. Okay? In terms of the molecular geometry, again, because the molecular geometry is just the atoms, right? That's going to be called bent. You literally can see it looks like a bent stick, doesn't it? It's literally bent. You can even give it like a funny southern accent or something if you want. It's bent. All right. Now, notice again the electron geometry, the number of domains, period, electron domains is 4 in all these. The electron geometry is tetrahedral for all these. When we start talking about non-bonding domains, this one has 1 non-bonding, 3 bonding, 2 non-bonding, 2 bonding. This one ends up being trigonal pyramidal when you're talking about the molecular geometry. Molecular geometry for this one, bent. Okay? And that's true whenever we look at 2 non-bonding and 2 bonding domains. It's that same geometry every time. Okay, this one here has 3 different electron domains, and they're all bonding, right? So if we have 3 ones, maximum separation is going to be trigonal planar. So that's a triangle on one plane. Okay, so that's trigonal planar. That's going to give you your maximum separation. Again, that would be the electron domain, the electron geometry, and the molecular geometry. Both would be trigonal planar in this case. Notice that every time we've been talking about these are always around a central object, right? So that's the geometry around this carbon here, isn't it? This oxygen here would have a different geometry because that has a different central point, okay? It would be like talking about the geometry around the center of your body versus your hand. Pretty different geometries, right? Same sort of thing with the molecule. So whenever we talk about geometry, we're always looking at a central point, and that's always defined. So in this case, it was carbon here. This one's oxygen there. That one's the nitrogen right there. Okay, so this right here is going to be 2 bonding domains around this, and that's going to be linear. What you're going to see is that anytime you have a triple bond, it always ends up being linear. If you have 2 double bonds, it always ends up being linear. Okay? Unless you have a very, very weird edge case. Okay, so carbon, what sort of shapes can we typically have? Well, we can have 4 bonding domains, tetrahedral, right? We have 3 bonding domains, trigonal planar. We have 2 bonding domains, linear. And those are the only choices. Okay? And so carbon actually becomes pretty easy to deal with when you're looking at these. Again, the non-bonding electrons have an effect on the molecular shape, but they don't get included when you're talking about what shape it is. Okay? They have an effect because they push everything away, right? They bend it, if you will. Okay? So the non-bonding pairs of electrons, they take up space, but they're going to be invisible in the molecule shape. Non-bonding pairs of electrons are going to force bonds closer together. And so if you have bonds with non-bonding electrons, they will actually squeeze those even further together. And the reason for that is when you have 2 atoms on each side, so when we're looking at a bond, what that looks like is like this. Has the electron clavin here, right? We have our nuclei here, and they're going to contain that to a very small space between them, right? What happens when you only have one side that's filled in now? It's spread out a lot more, right? And so what you actually end up seeing is it goes like this. It's spread out more. doesn't have another nucleus to contain it. Okay? And so everything else gets squeezed together whenever you have non-bonding pairs. And all the bonding angles go down. They all get squeezed. Right here is actually an example. So right here we have lone. Do you guys remember when we had just 4 hydrogens around the carbon? It was 109.5. Okay, that was before. When we have 1 lone pair, this bonding angle right here goes down to 107. When we have 2 lone pairs, 2 non-bonding electron sets, we're going to go down to 104.5. And so these are actually squeezing all the rest of the bonds together because they take up more room. They don't have that atom on the end to keep them nicely contained. Okay? Okay, let's talk about the molecular shapes of larger molecules. All larger molecules are just repeating sets of these Vesper shapes over and over and over. Okay? And so what you see here is if we just go through this larger molecule, this carbon right here is going to have a tetrahedral shape around it. Okay? This carbon here is going to be tetrahedral around it. This one right here is going to be bent around it. And so all together, what that kind of looks like is the carbons look basically like this. That's oxygen, that's hydrogen. Okay? And it zigzags. Because each of those are tetrahedral, so they're kind of zigzag altogether. Okay? All right. So again, all they are when we're looking at these structures is just repeated Vesper rules every single time we look at a central atom. Okay? Over and over and over. All right, so let's talk about electronegativity. So the electronegativity is the ability of an atom to attract the bonding electrons of a covalent bond to itself. This is going to be the electronegativity. The element with the greatest electronegativity in the periodic table is fluorine. Anybody know why it's fluorine? Notice the definition says bonding electrons. If you're a noble gas, do you bond? No. So noble gases typically don't have electronegativities. It's only if they can be forced into bonds somehow that they would get electronegativities. The electronegativity is going to typically increase as you move up to fluorine. The largest differences in electronegativity tend to be at the sort of top right. Things sort of scale down and stop changing as much as you go down and to the left. And so fluorine makes a big splash with approximately 4, okay, 4.0. It's actually 3.98. I'm going to tell you something funny. Chemists actually do have a sense of humor. I know. It's hard to believe, but it happens, okay? Anybody know why this is 4.0? If you get all Fs, what's your GPA normally? 0. This is all A's, isn't it? And so a chemist thought it'd be funny and said, well, I want getting F's to mean 4.0. So this is the only time you can get an F, and it's going to be 4.0. Mm-hmm. No, but you need to understand the trend. Yeah. So, the biggest difference is as you go down periods, you have smaller differences as you go left and right in a period. Okay? And that's the important trend right there. This is actually what gives you covalent bonds versus ionic bonds, by the way. Notice the metals have very low electronegativities. The nonmetals have much higher electronegativities. So when those things bond, the nonmetals just take the electrons from the metals because their electronegativity is much higher, so they pull the electrons much better. Okay? When you bond two nonmetals together, notice they're fairly similar electronegativities, and so one doesn't just wholesale take it from the other. Okay? You actually end up having to share, which is a covalent bond, isn't it? All right, and there you go. Look at that. We got covalent bonds and ionic bonds, the actual way to figure that out. Now, the inequality is going to occur when two different atoms are involved in a covalent bond. The electrons will be shared somewhat unequally if it's two different atoms. If it's the same atom, then they'll share them equally, completely equally. When two identical atoms share electrons, that's going to be what's called a covalent bond. When you have a difference in electronegativity between the two, you're going to have what's called a polar covalent bond. So this is when they're not shared equally. So when the electrons are shared equally, the bond is going to be referred to as a nonpolar covalent bond. Now, realistically speaking, we give some leeway to this. So like carbon and hydrogen, they don't share completely equally, but we typically refer to that as nonpolar, okay? And that's because it's not a large difference, and so it's not usually a meaningful difference, right? But an absolutely nonpolar covalent bond only happens when you have two of the same atom bond together, okay? Polar covalent bonds happen whenever you have an electronegativity difference that's usually about 0.4 or so different. So again, this is going to be even versus uneven sharing. Two hydrogens, when they share their electrons, they're going to share them evenly, okay? And so you don't have a difference in where the electrons hang out, and so you don't have any charges on this structure. It's all the same charge throughout. This right here is hydrogen bonding to chlorine, and what you see here is that the chlorine has a higher electronegativity. It's going to pull the electrons from hydrogen, right? And so the electrons are going to spend more time around the chlorine. Electrons are negative, so chlorine's going to have what charge? Negative, right? Hydrogen has less electron density around it, so it's going to have positive charge. Notice the name we had for this, the polar, as in poles of a magnet, right? So it's polar because it has a positive charge at hydrogen, negative charge at chlorine, okay? So these are what are referred to as partial positive charges and partial negative charges. They're denoted by this right here. This is the two symbols that you can use to denote them. This here is a small delta positive, small delta negative. Small delta means partial. And so partially positive, partially negative. Okay? Capital delta, by the way, means whole amounts. Positive, negative. In case you're ever wondering. So that's whole amount changing, capital delta, partial, small delta, lowercase delta. This right here is also another symbol you can use. You put a plus sign on the side that's going to be positive, and an arrow pointing where the electrons tend to spend most of their time towards. Okay? All right, so again, this is the lowercase delta that I was talking about in case you couldn't see it before. Delta negative, delta positive, delta negative, partially negative, delta positive, partially positive. Whenever you have this charge separation, again, that's going to mean that bond is polar, okay? It literally has poles of a magnet, right? Positive and negative. When you have a nonpolar bond, that's going to be where it shares equally, and you don't have any poles on that bond. No positive, no negative side. It's just overall same charge throughout. We can predict the type of bond likely to form by taking the difference between the electronegativities of those two elements. That difference in electronegativity, that's going to tell us whether it's going to be polar covalent or non-polar covalent, okay? Or if we're going to get a full-on ionic bond. Now, this right here is actually those separations. So 0 to 0.4, that's going to be where you're non-polar, okay? That's the cutoff we typically call. When you're 0.4 and greater up to 1.8, you're going to be what's called a polar covalent bond. You're still sharing the electrons, but you're not doing it equally. And so you'll have poles, you'll have charges on each end. This one right here, 1.8 up to 3.3, that's ionic. At that point, you're just going to have one take the electrons from the other because it holds on to it so much better. Okay? Everybody okay with that so far? And so this is ionic bonding. They don't share the electrons at all. One takes from the other. Okay. So again, 1.8 or more, this is going to be a transfer of electrons. Less than 1.8, they'll share their electrons. That's where we get the covalent bonding. It may not be even, but they'll share the electrons. All right, so is it possible to distinguish ionic bonds from covalent bonds by looking at the types of element presence? Metals versus nonmetals? Yeah, right? Metals have lower electronegativities, and so if it has a metal and a non-metal, you're going to have ionic bonding, right? So again, to distinguish between nonpolar bonds, slightly polar bonds, and strongly polar bonds, you need to remember two major facts. Fluorine is the most electronegative of all the elements. So anything bonded to fluorine that's a metal or in the lower end is, they're all going to be polar in some way. Hydrogen with fluorine is going to be highly polar covalent bond. Okay. Electronegativities are going to increase as you move towards fluorine on the periodic table. So if you have something pretty close to fluorine, it's going to be probably polar, but not super polar. If you have things that are like oxygen, that's typically going to make polar covalent bonds. Okay. Once you get to carbon, it typically makes non-polar covalent bonds, as long as it's not bonded to something higher electronegativity. Right? So the farther apart two nonmetals are on the periodic table, the greater the polarity of the bond between them. The exception of this rule is C and H, because H kind of has to be put somewhere that's weird. So hydrogen actually has a fairly high electronegativity, much higher than you'd expect from its position. Okay? And so carbon and hydrogen is a non-polar covalent bond. And that's one of the ones you kind of need to remember, because you might get tripped up at first. Okay? So remember, hydrogen has like a 2.1 electronegativity. It's a lot higher than you'd expect. Okay? And so carbon, hydrogen, nonpolar. All right, let's talk about the polarity of molecules. Now, molecules can be polar or nonpolar. Again, it's just the presence of poles, right? You have one positive end and one negative end molecule. That's all that matters. So a polar molecule is going to have an uneven distribution of electrons over the entire molecule, making it positive on one end, negative on the other. A nonpolar molecule is going to have an even distribution of electrons over the entire molecule. There won't be a positive and negative end. That's all that is. So for molecules that contain two atoms that are connected by a covalent bond, the polarity of the molecules, simply the polarity of the bond. You don't have to worry about anything else. Okay? So like HF is polar bond and a polar molecule. That's it. No problems. Okay? When a molecule is composed of three or more atoms that are connected by several bonds, we have to consider whether those electronegativity difference will cancel each other out. Because if you have equally pulling in all directions, you don't actually move anywhere, right? You won't have any buildup of charge on one spot. Let's see an example here. Okay, so this is carbon dioxide and this is water here, okay? Okay, so notice they have polar bonds on both of these, right? Carbon oxygen is a polar bond. This one here is a polar bond. Everybody okay with that so far? Yeah. So the bond here, that's polar bond. This is a polar bond as well. This one is also a polar bond, also a polar bond, okay? So we have two sets of polar bonds in both these. But what do they look like three-dimensionally? Well, if you look at carbon dioxide here, this is linear. Can everybody see it okay? Water, on the other hand, is bent. So when we look at these bonds, these ones here, they're pulling in opposite directions equally, aren't they? And so they're going to cancel out. Can everybody see that okay? So you don't have two poles. You're actually going to have negative on the outside, positive on the inside. So it doesn't have two poles. It just has same overall. So that's non-polar as a molecule. The bonds are polar. The molecule is non-polar. Okay. This here, well, they're not going to fully cancel out, are they? See, that oxygen is going to end up negative up here, isn't it? And you're going to end up with a positive charge down here. And so that one is polar overall. And so water is a polar molecule. Okay? And that's what that molecular dipole looks like. So di meaning two. So this molecule has two poles, right? Has a positive charge down here. It's this red one. Has a negative charge up here near the oxygen. Okay? And that's, again, the molecular dipole. These are the bond dipoles. These are the molecular dipoles. Okay. Are we keeping those straight? Okay, so again, it's how they add up that determines this. This is going to be important because do water and oil mix? No, they do not mix, do they? Why do they not mix? Anybody ever heard an explanation for it? Have you heard like dissolves like? No? Okay. So the reason they don't mix is water is polar, right? And so if you have a bunch of magnets and you throw them in a baggie, what's going to happen to them? They're all going to snap together, positive, negative, over and over, right? Okay. Now, what happens if you put a bunch of neutral stuff in with it? Is that neutral stuff going to snap together inside of it? Anybody ever have Legos and they have magnets in the same bag and they shake them? Or marbles and magnets when you're a kid? No? Okay. So think about this in your head, okay? We have the magnets together. What's going to happen to the magnets? They're all going to snap together into arrangements, right? That's going to be like the waters, okay? What happens if we put something that's not magnetic in there? Is it going to get included? No, all the magnets are going to snap together and it's going to exclude all the neutral stuff, right? The stuff that's not magnetic, okay? And so when you look at oil, it's nonpolar. It's neutral. It doesn't have magnetic poles, okay? And so what happens with water and oil is that the waters all snap together and then the oil either sinks or floats on the top and doesn't actually get incorporated, okay? That's why if you ever go to the gas pump, everybody's been to the gas pump, right? You see the puddle on the ground from the rain. What's on the top of it? The shiny stuff, right? And that is the oil and gasoline, okay? And that's because all the water snapped together and they squeezed out all the oil and gasoline, okay? Okay, we'll talk more about that, which is intermolecular interactions later. Okay, did anybody have any questions about this polarity? Poles. Molecular pole. Poles on a molecule, right? It's the addition of all the bond dipoles together. Bond dipoles are along a bond only. Okay, they're per bond, right? If you have opposing bond dipoles, they're going to cancel out, just like if you have opposing forces. So if I pull my two hands against each other equally, does it move anywhere? No, right? Same thing happens when you're talking about bond dipoles. So if I have bond dipoles that are directly opposite of each other, they're going to cancel out. Another example of this is if we look at some of the examples of things we've written so far, we had our CH4, right? Remember, it looks like this, right? Coming out, coming away. Okay. So all of the hydrogens would be pulling in different directions, wouldn't they? And so that's all completely non-polar. They just cancel out completely. If you have a similar structure with, let's say, fluorines on it. Okay, again, that's that tetrahedral structure with fluorines, okay? Fluorines will have bond dipoles. They'll actually be like this for each of the fluorines. Okay? But notice they're all going to pull in different directions, aren't they? They're going to pull equally in every direction. And so if I'm pulling equally in every direction, are those electrons going to form poles? No, they can't they? Because they're being pulled equally in every direction. So all of these fluorines actually cancel each other out. So again, the bonds are polar, right? The overall molecule is non-polar, okay? Because they all cancel out. Let's look at this one real quick. So this one is trigonal planar. And again, we have bond dipoles that pull like this. Okay? The overall dipole is just going to be straight like that. Okay? These these ones partially cancel each other out, but you get your overall flow of electrons this way. That's going to be negative. This is going to be positive. Okay? All right. Did you understand? Anybody get lost? Okay. Got lost? Practice. Try out some problems. See if you can do it okay. Can't understand it? Please talk to me. Talk to tutors. Okay, so let's really quickly do the last questions. Please note again, these are the study guides. There's the exam coming Monday. There is also a nice little review assignment. Those review assignments all together are actually worth about half an exam worth of score. Okay, and again, remember the exam is scaled, but it's only a limited scale. So if everybody makes a death pact, they're going to regret that. Okay? Okay. It does happen, by the way, in case you're curious, where all the students make a death pact. Let's all do Fs and can't fail us all. This college, I can definitely fail everyone. So, yeah. Okay. So draw the Lewis structure for NO2. How many electron domains, clouds, are around the nitrogen? What's the molecular geometry for that? Okay. So try your best to draw those out. I'm going to give you another minute or two. This one's probably going to need you to do my full procedure for the Lewis structure. Okay? This one will be difficult to get with just using this one single bonds, this one double bonds. Because not everything is going to perfectly have single and double bonds like you would want. Bring it alcohol. That. Okay. In case you're wondering, I actually had a video, if you look through my Lewis structure videos, where I did this exact one. So, as a reminder, there are other videos that can be helpful to show you things on that YouTube channel, including videos covering some of your homework problems, actually. So. The homework problems ones can be a little bit difficult to figure out. Okay. All right. So go ahead and start getting your answers ready. I'm going to see how you guys do on this one. And I'll turn around and I'll help you all out. Okay, so go ahead and get an answer in. I want to see how much you struggle if you do. Okay. And if it's not coming up on the deal, you need to shift it around and get your fingers removed from it so it can pick up. Okay. Go ahead and get an answer in for now, if you haven't already. Okay.
We can't see if we left it.
Really? Okay. I have 10 people. 8, 10. I'm missing one, I guess. Okay. We'll redo the answers in just a second. Looks like a few people got it. Okay. So whenever we redo the answers, just hold up what the correct answer is, and we'll have to see why that's not doing that. Okay. So how do you do this, Mom? what's the first step? Add numbers of electrons, yeah. So we go NO2 right here, and nitrogen has, very good. Oxygen has, perfect, very good. And that's going to give you a total of, yeah, so we got 12, 17, my goodness, that is odd. So this one has an odd number, where we were talking about before, where you have only one electron. Okay, what's going to be in the center? Nitrogen. It's the furthest away from being null, right? What's going to be connected on the outside? Oxygens. Yeah. Put a single bond each for now. And we've used how many electrons so far? Okay, and so that's going to leave us with 13 remaining. All right, so now we distribute the electrons on the outer things, right? These oxygens. Not on the inner yet. We're going to leave that for the end. Okay. How many electrons do you want on those oxygens? Really on all the things in this one. It needs to be 8 electrons total, right? Okay. And so we need to put 6 more on this oxygen here. That'll give us 8 on that. 6 more on that one. Now we've filled all the outside ones, right? We've used up an additional 12. So we have 1 remaining though. That one's going to go on the one in the center, because it's the only place left we can put it, right? And so we put 1 on the center because that's the only place we can do it. That uses up all of our electrons. Can I put 2 on the center? Did I have 2 electrons to put? No, so I can't put 2, right? I don't have an extra electron. Okay? People tend to be tempted to do it and then do that, and then obviously they can't answer it. Okay, now the next thing I need to do is, do I have full octets on everything? I have full octet there, but not there. So I need to add electrons into the center until I get full octets, right? Okay. And so I'm going to take my handy dandy finger, I guess, and erase it with that. That's one hand, I guess. And I'm going to move this into double bonds until I have a full octet on the center, right? Okay. So we move 1 pair into a double bond. Doesn't matter which side I do. No. Doesn't matter which side I do. It's the same thing either way. So I have a double bond there. How many electrons do I have now around the center? 2, 4, 6, 7, right? I can't put any more because that would go over 8, right? I'll have space for that. And so this is the structure. How many electron domains are there? 1, 2, 3, right? And so there's 3 electron domains. 2 of them are bonding, and 1 is non-bonding. And so that would be 3 electron domains, right? And then 2 bonding, 1 non-bonding. That's going to be what shape? It's going to be bent, right? Okay. So go ahead and get your answers ready. Get those in, and then you'll have to get to the next class. Okay, I got everybody in that corner. I got all of you. Yours was wrong, though. You did the wrong answer. I didn't get you. You'll have to come a little closer with here.
I mean, I answered that.
Did you answer it correctly the first time?
Yeah.
You had the correct one. Yeah. There you go. All right. Did you answer it correctly the first time? Oh, okay. Yeah, you're good. Nope. Do that one on your own. I'll go ahead and give you the answer for that. It's 1.2 times 10 to the 24th. Double check that you understand how to do the mole versus molecule conversions. Okay? Okay. here, folks. Double check. We have lab on Friday.
Yeah, I know they're not.
Lab will likely end early if anybody wants to ask me questions on Friday.
We're in a few tips to the house, so. I got a little bit out for you.
Right.
Well, the purple, they're like, I've not